So we continue now. So this is the last, somehow the last step in this, in the formal part of six functors formalism. So let me recall that we have introduced what I call the pre-motivic triangulated category. Which means shortly that you have a family of triangulated category indexed by base schemes. You have certain operation f upper star, f lower star, p sharp for p smooth, tensor product, internal which satisfies some basic properties. I said smooth base change, and smooth projection formula. All this is basic, and the idea in motivic homotopy theory is that it's easy to get these kinds of things. And the example we have seen one in Oliver's talks. This is the stable homotopy category, and I advertise another one, the A1 derived category of sheaves for some topology T. Say, maybe I should write S. T of S for base schemes. And here the topology can be, for this basic property, topology can be arbitrary, but usually I'll take, in the end, here I'll take Nisnevich and et al. And yeah, DA1, so this means the P1 stable A1 homotopy category. We have seen basic axioms that we can ask that these pre-motivic triangulated category satisfies. So this was the homotopy property and stability property. Okay. Once you have that, just to finish with a recall, then using this definition for P x to S smooth equal to P lower sharp, P upper star of a constant object, and this is just P sharp on X. Then you get a reasonable notion of pre-motive, say, and you can do what we usually do in this stable homotopy category. Okay? So the aim of today is to introduce the last axiom that I need to get the six functors. This is the so-called localization axioms. Unlike this one and this one, it's really a hard property which implies a lot of things, and in particular all the formalism, and it relies on some big theorem of Morel and Wojcicki. Yeah, maybe I'll go on here. Okay. So I start with the formulation of this axiom and some basic application of it. So let me use this context. So I will always be in such a pre-motivic triangulated category. You don't need, for what I will state, you don't need these two axioms, homotopy and stability, but in the second section I will use these axioms. So we just take a pre-motivic triangulated category, and now look at some closed immersion, Y from Z to S, with complementary open, U denoted by G, U, E, S minus Z. Okay, so we have basic already with these two assumptions, smooth Bayesian and smooth projection formula. We have some basic facts which are automatically true in this situation. And the first one is that if you look at this map, which is just the adjunction obtained by adjunction, then it's an isomorphism. So this is a consequence of a smooth Bayesian property for J. So it means that J lower sharp is fully faithful and T of U embeds into T of S. Okay, dually, we will have that G lower sharp counit is also an isomorphism. This is just because this functor is left adjoint to this one. No, right adjoint, sorry. Right adjoint to this one. So if this one is the identity, then his right adjoint is also the identity. Okay? And we have also another thing is that if you take Y upper star J lower sharp, and you have to think of this as J lower shriek, then this is 0. And again, it's a consequence of a smooth base change property. So for those who knows the axioms of 6 gluing functors, which appears, for example, in BBD, then we are missing some properties to get the 6 gluing functors, and this is what the localization axiom asks. So maybe first definition, I will say that the localization property for I holds, say loc I holds, if the following two properties are true. First, you ask that the counit map from Y upper star to Y lower star to the identity is an isomorphism. Okay. This is the first part, and the second part, which is maybe even more important, you ask that the pair of functor J upper star, Y upper star is conservative. Okay, so let me picture that. So we have TZ, we have some restriction T of U. And so this last axiom tells you that you can study locally, in some sense, the object in T of X. To test that an object is 0, you can just look at its restriction to U and at its restriction to Z. So this axiom is really important because it allows you to study object in the triangulated category locally. This is something which will be used a lot in all the following. Okay? So naturally now if I want this property for all closed immersion, so the final definition is that T satisfies the localization property. If so, there is something that you have to add. First, you add that the value of the category of the empty scheme is just the 0 category. This is just for formal reason. Gabber is not here, but I need to put this, otherwise I will run into stupid example, counter example. And then you also ask that for all closed immersion, I localization property for I holds. Okay. So just note that so we have seen that with some support axiom we can build the F lower shriek functor, but I have not stated, but we are missing some properties, such as, for example, the proper base change theorem. And you can see that, in fact, this requirement here is a particular case of a proper base change theorem for Y lower star. So already you see that this localization property gives you some preliminary part to this important theorem, but I'll come back to this. Okay, so maybe the main consequence of this property is given by the following proposition, which is essentially a good reading of Beilinson-Bernstein-Deligne. So we assume that T just satisfies the localization property for a particular immersion I, closed immersion with this notation here, then the following property will hold, and this will maybe it will recover classical formulation. So first of all, there exists a unique distinguished triangle of the following form. There exists a unique distinguished triangle J low sharp J upper star, say of an object K, goes to K, goes to Y lower star, Y upper star of K, and here I have a boundary Okay, so will just be the co-unit of the adjunction and the unit of the adjunction. And again, you have to think of J low sharp as J low shriek. Okay, so the unicity argument concerns this map here. Secondly, you can also show this is not, I'm not sure it's directly in BBD, but Y lower star admits a right adjoint, which I will denote Y upper shriek, and we have a unique distinguished triangle maybe, which goes like that: Y lower star, Y upper shriek of K goes to K, J lower star, J upper star of K, and there is some boundary here. Again, this will be the co-unit of the adjunction and the unit. Okay, this is just the dual, in some sense, of this. And so this is the classical axiom that you found in BBD. They are obviously very useful. Basically, they tells you that T of S is a gluing of T of Z of T and T of U. I mean, T of Z is, for example, you can state it like that. T of Z is a full subcategory, full localizing subcategory of T of X, and T of U is isomorphic to the Verdier quotient. You can state it like that if you want. Okay? There are also more classical, there are also other consequences of loc I. I won't tell you all of them because I have not much time. Other easy consequences. So first of all, you can show that T satisfies the BG property that I have stated earlier, meaning that the image of a Nisnevich distinguished square by this functor M of S is homotopy Cartesian. But I won't state it here. I state a stronger property. Actually, T satisfies the CDH, say it like that, descent property. So what is it? It means that assume that you have a so-called blow-up square. So this is a Cartesian square of schemes such that P is proper, I is a closed immersion, and P is an isomorphism over X minus Z. Maybe I should have, well, okay. Maybe I should have, sorry, I should have used this letter. S S here. Okay, so then you can formulate the so-called CDH descent property by saying, so you cannot really use the functor M of S because, for example, B of S is not smooth, but you can still use the dual object. So it means then that for any k in T of S, the following diagram is homotopy Cartesian. So you can go from k to y lower star, y upper star. You can also go p upper star, p lower star, p upper star, and from there you can go to, say, H, where H is just the composite map here. So these maps are just obtained by the adjunction map. So for Y, for P, here I should maybe introduce this. This is derived from the adjunction for K, and here adjunction for Q. Oops, sorry. So the conclusion is that V square is homotopy, is a homotopy pullback, or is homotopy Cartesian or co-Cartesian. It's the same thing. Okay. And the thing is, how do you check this? Then, but to check that this is homotopy Cartesian, because of this conservativity property of J upper star, Y upper star, you can take the pullback of V square either over Z or over the complementary. Over Z, then it will be trivial, and over the complementary also because of this property, P is an isomorphism. Okay? So CDH descents follow formally from the localization property. Similar statement for what? So you look at V square and you take so V square lives in T of S, okay? And to check its homotopy Cartesian, you can because this pair of functors is conservative, you can take the pullback. You can take the reduction of a square over U or over S. But in this case, the square here is trivial in each case. Either it's identity or an isomorphism and empty set here. Yeah, by the way, you see that you also use this property that the empty set is 0 in this argument. Okay, maybe a last trivial consequence. So this is the first one. Second one is the following. You have base change formula with respect to, so let's, Y again, close immersion, Z to S. In some exercise, I had made you constructed this functor. Say you take some morphism F from T to S, for example, and you want to compute this, then you can exchange these functors and you will have something like that. F prime plus star for the obvious Cartesian square. And the localization property for, I think I is enough, imply that this exchange transformation is an isomorphism. So here I is proper. So you see that this is a particular case of a classical proper base change theorem in SGA4. And similarly, you also have that there's an exchange between Y lower star tensor product, which is the following: Y lower star of C, say M0 tensor M, or maybe I change notation. It goes to y lower star M tensor y upper star of n, like that. This is canonical. This is another extended transformation. And again, the localization property implies that this is an isomorphism. Okay? The proof of this is quite obvious. Each time you just use this property, that it's conservative, and also you use these kinds of things that you have such isomorphism or zero, and then you reduce to the case where either it's the identity, it's the obvious isomorphism, or just zero. Okay? This is quite formal. Okay, maybe now I'll go into the direction of proof. How do you get this localization property? Unlike the other axioms like homotopy and stability, maybe I keep this. This is really a theorem. So, what can you do to reduce it? So again, I take a closed immersion y, say from S to Z, from Z to S, and take the J to be the open, complementary open immersion. Then this property that I stated is equivalent to the following two properties. First, you just have to prove that y lower star is conservative. Remember that the localization property implied that it was fully faithful, actually, but you just need to prove it's conservative, and also that for any object k in T of S, the following sequence is, say, homotopy exact. Okay, you can reformulate this by a Cartesian square if you want. This amounts to prove that J that V square is homotopy Cartesian. Okay? This is equivalent. Okay, so you see, you essentially, when this is homotopy exact, then you will get this distinguished triangle here, and then you can use these two properties to show that actually the pair of functor is J upper star, Y upper star is conservative. So this is formal. I will not prove this, but now. So this is how you prove concretely this axiom. So the main point, first the main point is really the point B, because the point A is somehow formal. Point A is maybe not formal, but easy. It's not formal. If you assume that T is state generated, meaning recall that in some sense K is always isomorphic to a homotopy colimit. object like that. And maybe also you assume that the stability property holds, so that this twist here is not really important. Okay, so also Oliver had recalled us the definition. You asked that the functor MSXI shifted by something is conservative. Then if this all, then point I is automatic, because so if you want to prove that, so you assume that y lower star k is 0, and you want to prove that k is equal to 0, okay? But this is to prove that k is equal to 0, because you have generators like that. You are reduced to prove that so k belongs is a primotive, say, over z. And you just have to check that in Tz, if you take any object z0, x0, in like that, you want to prove that this is equal to 0, okay? Where x0 over z is smooth. Using the localization property, using the, maybe I should have said that also, stab and the BG property, sorry. And using the BG property, you can show that this is local in Z. So, for example, you can assume that z is affine, and x0 also is smooth affine. Then in this case, because it's smooth, you can assume that this diagram x0 S can be filled. So there exists P smooth, and x0 is the restriction of x over z. Okay, so this means that mzx0 is isomorphic to y upper star of ms of x. Okay? Then if you have this property, you can compute this. And this is equal to ms of x twist I shift n with coefficient in y lower star. You just use the adjunction of k, because y lower star is the right adjoint to y upper star. Okay, but this is 0. And this is finished. Okay. So you just use the fact that you can lift smooth schemes over closed immersion in the affine case. And it remains a property B. For still assuming this assumption here, you see that you can take k. Also, there's just one reduction for B, which is universal. You can replace k by some msx. X over s is smooth. And the twist here is not important, because I've assumed that twists are invertible, so they will commute with every functors, and I can just forget them. And by the way, the twist of some homotopy Cartesian will be homotopy Cartesian. Okay. Okay, but there's not much that we can do to reduce formally these axioms, and now I must state the theorem of Morel and Voevodsky, which says that in the A1 unstable, A1 unpointed homotopy category for any, for any space X, so simplicial sheaf. The square, this one here essentially is homotopy Cartesian. So because it's unpointed, the formulation is like that. You have here J sharp J upper star of X, X, Y lower star, Y upper star of X. And here instead of 0, you put the object U, represented by U, okay? So the conclusion is that this square is homotopy Cartesian. Okay. So first, I will give a very rough idea of the proof, but I must first give a reference. So this is the book of Morel-Wojewski, A1 homotopy category. This is the state theorem 3.2.21 in the last section, last part of the book. The proof contains at least some mistakes, stupid mistakes, which can be corrected. So that the only completely correct proof that I know is that of in the book of Joseph Ayoub, his thesis. So it's in asterisk, first volume, and it's theorem 4.5.44 for a correction of a mistake here. So what's good with this proof here is that it's short. It's around 1 page, but very stupid mistake. What's good here is that it's completely correct and it's very general, but the proof is quite long and involved. So there's 10 pages. In A1 homotopy, this is the only result that really prove localization. Then all the localization results for other pre-motivic categories are derived from this one. So it's really a pillar of the relative homotopy, A1 homotopy theory. And the proof is quite, so just a word about the proof. Yeah, maybe I just have the time. So I have no time to do all the proof, just give you some aspects of the proof, not everything. So as I said, you can restrict to a case where X is representable, and then you have to prove, assuming X is some scheme X for X over S smooth of finite type, as usual, you have to prove that the push out, like that, of this going to Y lower star X cross S Z is an A1 equivalence. So yeah, you look at the square at this. Oh no, sorry, at this square here, where X is X here. You compute J lower star J upper star, and this, and you replace the square by here just taking the homotopy push out of, or just the push out actually in the category of sheaves of simply short set of these two maps here. Okay. Now to do that. I'll tell you a part of a reduction where there is geometry which is involved. You can assume by some very tricky argument, very beautiful argument, that you are in this situation. Not only here you have some smooth map, but you are given here a section phi. Right, so this is the closed immersion. Okay. Then using Nisnevich descent, you can assume that S is Enzelian. So that we call it phi naught. So that phi naught extends And of course, if S is S local and Zillion, and Z also local and Zillion, or if it's empty, it's trivial. So you can assume that phi naught extends to phi from S to X section of P. Then using again Nisnevich descent and a classical trick, you can reduce to the case where X is AN of S, and the section 5 goes through the zero section. And the section 5 is the zero section. Okay, and then in this case, it's not tautological, but you can really get an explicit A1 homotopy to conclude. Okay? So I'll tell you that because this first reduction step will be an obstruction to get the same proof in the case of sheaves with transfers. Okay, so once you have this property for the A1 homotopy category, then you can derive localization for many triangulated pre-motivic category. So, yeah?
How this square looks like in this very particular case.
What do you mean? AN?
There is some geometry. Some geometry.
So it looks like AN S modulo AN of U going to Y lower star AN of Z. So that you can see that by an easy argument shows you that by A1 homotopy you are reduced to prove that S over U to Y lower star of Z is an isomorphism. But even this property is not so easy. So you really have to, this is why I'm adding something, you really have to use the argument of Wojewski, where he passed from Wojewski and Morel, where they pass through some intermediate sheaf build out of this. Okay, so in our two basic examples, you can easily conclude, more or less. So, main examples which were derived in the physics of Ayub were T equal to SH and the A1 T R for T finer than Nisnevich. And how do you do that? So this is just because you have functor like that, HA1 to SH. So there is, actually this is a pre-motivic adjunction. So this category is not triangulated, but it's still a pre-motivic category. So this is just the infinite suspension. And you can show that sigma infinity commutes with Y lower star. So that, as I said, you only have to prove the fact that this square is homotopy Cartesian, even when K is representable by some smooth scheme. Then you apply this square here, and you just apply sigma infinity. It commutes with functors, and so the image by sigma infinity is homotopy Cartesian here, and you get localization. Similarly, you have a kind of Dolkan adjunction from SH to DA1. Let's do first the Nisnevich case. So derived from the classical topological Dolkan equivalence, you get such an adjunction. This is really an adjunction of pre-motivic category again. And you get also that K commutes with Y low star. Okay, so you use the same argument. And finally, if you pass from Nisnevich to et al. Topology, you'll get also a pre-motivic adjunction such that the left adjoint commutes with Y low star. Okay, so we get the localization property in all these examples. Okay, now, so we have seen easy consequences of this property, but now we'll see the main consequence. And this is the relative purity property. So this will oh. Can I do that? I'll go. Sorry. Is it still working? Okay. So, this relative purity property is really important. It's one of the key part of six-functor formalism, and here it will be a consequence of our axiom. So we assume that T satisfies, just to simplify, stability, homotopy property, and localization. In this case, we say that T is motivic because, as we will see, these three axioms are sufficient to get the full six-functor formalism. This was first remarked by Wojewski and proved by Ayub, of course. So we assume in this case, and now we will relate this abstract functorial setting with more classical consideration, I think, in my opinion at least. So just first I use some notation. Q, I consider some closed dimension I and assume that P and Q are smooth. Like that, then I will denote MSX X minus Z to be the homotopy cofiber of a canonical map from X minus Z MS of X. So if I want that this is well defined, maybe I should add that T is the homotopy category of some model category, or T is an infinity category, then there wouldn't be any problem to have this canonical and functorial. This is what you have in practice, of course. Example, as you know, if X is equal to E is a vector bundle, I equal to S, the zero section, then this object is nothing else than the Thom space. And so S Thom of E. Okay. But consider over the scheme the base scheme S. So this really lives in T of S. Okay. Then in this abstract setting, I can also formulate the theorem of Morel and Wojewski, what we have already seen in one of Oliver's talk. now theorem, essentially due to Morel-Wojcicki, there exists a canonical isomorphism. In this situation here, between this motive, this pre-motive, sorry, in T of S, and so the motive of the Thom space of a normal bundle of Z in X, and as in the classical case, the map is canonical, it can be explicitly described. It goes to some pre-motive of some deformation space. And the statement is that these two maps are isomorphism. The deformation space, you can take it to be the blow-up of Z cross 0 in A1 of X, for example. Okay, the proof is axiomatic, so that you use only the homotopy property and the BG property. BG property is a consequence of localization. Okay, so now what's the link with these classical things, with functoriality? So there is an easy dictionary. Now you take a particular case, link with functoriality. I will take some smooth map and a section. Okay. In this case, I can really compute the following composite functor. If I want to understand this functor, F sharp composed with S lower star, what will I do? I will use the projection formula. So this is really like in cohomology, like you will do that in cohomology. So of course, you can write this because F composed with S is the identity, okay? And tensoring with the unit does not change anything. Then you can use the projection formula for S, and we have seen that it's a consequence of localization, and it will give you F sharp. Here you have S lower star of unit object, tensor F upper star of K, and then you can use the smooth projection formula for F, and this is the same thing as F lower sharp S lower star unit object tensor K. Okay. If you think of cohomology, you will instantly find the analogy. And now the fact is that we can compute this object here, F sharp S lower star, by using the localization triangle. Maybe. Can I erase this here? So if J is the complementary, X minus Z S is the complementary open immersion. Remember that you have a triangle like that, J upper star, J upper star. I apply it to a unit of X, and this goes to S lower star, S upper star, a unit of x. Okay. In other words, I can write this as m over x of x minus s. This can be written like that, and this is just s lower star 1 of x. Okay, so that if I apply p lower sharp now f lower sharp, sorry, to this diagram, I get an isomorphism. Give you so the motive of x of x over x minus z is canonically isomorphic to f lower sharp s lower star 1 over x. So that in the end, I get a purity isomorphism associated with this situation, f and s, which goes from f sharp s lower star of k isomorphic to tensor k. This is x minus s. So all these isomorphisms are formal, and then I use the purity isomorphism of Morel and Verivetsky, and I have this, the Thom space of a normal bundle of a section S tensor K. Okay, so with the localization property, I can compute this functor, and also with the help of this isomorphism here. Okay. Now I can define the purity transformation. So, definition. I take f from x to s to be smooth and proper. Then I consider this diagram, so I can take the pullback square, use some notation, and I can also consider the diagonal immersion of x in x cross c. This is a section of f2. Then I will denote some relative purity natural transformation, which goes from f sharp. This is f sharp composed with f2 star delta star because this is commutative. Then I can exchange along this square delta, if you want, here, sharp and star, and this will go to f lower star f1 sharp composed with delta star, and then I can use the isomorphism constructed here precedingly for f1 delta, because delta is also a section of f1, and this is f star tensor product with Thom space. So the normal bundle of delta is nothing else than the tangent space of f, tangent bundle of f. And here I should take tensor product with this. Okay, so one of the axioms of a six-functor formalism is that this map here is an isomorphism, and this is what you can derive from the axiom that I have supposed here. So I give you a solution now, or at least a reduction of this property. So actually the thing is that the fact that this isomorphism, we have an isomorphism like that, is really related with duality, and strong duality that Oliver has stated, has mentioned in his talk before. So this is why I use smooth and proper. Okay, and the thing that you can realize is that the fact this is an isomorphism is actually equivalent to the fact that the motive of X over S is rigid, admits a strong dual. But there is something we must be more precise than that to state this, and I'll do it here. Okay, so how do you relate this morphism with strong duality? So first you construct a pairing. So to do that, so we are in this situation, you look at the motive of X cross Sx over X here, and you have a projection to Mx cross X modulo this cofiber where delta is the diagonal of X over S. Okay, and by Morel-Wojcicki theorem, you know that this is also the motive over X of the Thom space of, again, the normal bundle of a diagonal, which is nothing else than the tangent bundle of F. Okay. You work over X, so stability property implies that this is tensor invertible. So you know that for the stable homotopy category, and it works formally the same here. This is because we are looking at a vector bundle over X, really. So we get something like that. Tensor motive of X of the Thom space of the inverse. I will denote it here by minus TF, something that Oliver has already done, but it goes to the unit object over X. Now I apply F low sharp to this, use the fact that this is the same thing that F upper star of the motive of S of X, and using the projection formula, I will get a canonical map from the motive of X over S, tensor the motive of S, of the Thom space, but seen over S, minus TF. And here I have F sharp 1X, which is nothing else than the motive of S of X, and I can project by F to the unit object of S. Okay, and this is my pairing mu. Okay, with this notation, okay, we'll use this blackboard. Can you see it here? You have equivalent condition. Some kind of proposition or theorem, I don't know. Under the assumption homotopy, stability, localization, the following conditions are equivalent. First, you ask that this transformation PF is an isomorphism. And secondly, you ask that the motive of X over S is rigid. I defined that in the previous talk. And you have to add something, the transpose of this map, mu prime, which goes from Thom space to the internal Hom, to the weak dual, say, of MS is an isomorphism. Okay. Okay, so this is formal once you have obtained everything. You show that, but there is a trick due to Ayub actually. You have to show that showing that P of F is an isomorphism is the same thing after composing with F upper star, all the functor here. And when you have done that, you can see that the transformation constructed here can be identified with this map here. So you get that after applied to some objects, and so you get the equivalence of conditions. So yeah, I'm a bit short in time. So
what you do in this board, that does not assume F is proper, right?
Here, no. That's right. But if X is not proper, then you won't have this property here. That's what Oliver mentions. You don't have strong duality for, like that. Okay, so you can apply this. How can you get these kinds of assumption? Usually this is obtained by constructing some isomorphisms. And so if the cohomology HNMXT, which is on in TS MSX and if this cohomology theory is oriented in the sense of Panin-Smirnov, then you can show property 2 only with the axioms homotopy, stability, and so on, and get that PF is an isomorphism. Recently, the fact that you can construct isomorphisms without orientation has appeared, and I think we could use that to prove also directly this proposition. But actually, the first argument where this is proved here is in the thesis of Ayub. So I have not the number, but it's in the asterisk. And this is something that Wojewicki did not publish. So actually, Ayub directly proved this isomorphism. He did not consider this duality assumption. Okay. Okay, so I have not much time. But now once you have something like that, you have identified F lower star with some F lower sharp when F is smooth and proper. Then you can deduce. Maybe I said something. So the conclusion of Ayub asterisk is that one always holds. Then you can deduce the support property, for example. So recall the support property consisted to show that J lower sharp commute with F lower star for F proper. So you can show that the localization implies this result when F is a closed immersion. Using the localization property, you can reduce to a case where F is projective. When F is projective, then it's composed by a closed immersion and the projection of a projective space. So you reduce to the case where F is proper and smooth. When F is proper and smooth, you can compute the F lower star. The term space will go on the left here, and it's a F lower sharp. F lower sharp commute with J lower sharp, and you get it. Okay, and so once you have that, you can construct F lower shriek, and then you can prove the other two axiom, which I will state just for completeness. Sorry to to be late. So, and you can prove finally also then that you can exchange. So let's P upper star F lower shriek. So recall F is separated of finite type here. You can exchange upper star and lower shriek. Is an isomorphism. So this is what's called usually the proper and smooth base change theorem in one assertion. And also you can prove that F lower shriek M tensor F upper star of N is isomorphic. Maybe the arrow goes in the other way to F lower shriek of M tensor N is an isomorphism. And again, to prove this, you reduce to the case where F is smooth, and you use this property here. Also, maybe I should say that, so these are 1 second. Last property is general purity. You don't need F to be proper. If F is just smooth, then you have an isomorphism between F lower sharp and not F lower shriek, sorry, and not F lower sharp with F upper star, lower star, term space of the tangents of F. Okay. Yeah, I think I will head in here.
Okay, let's think that quickly. So questions, comments?
So my question is on the previous blackboard. Why do you need rigidity to say that these two properties are equivalent, 1 and 2?
What's the implication that you want? The fact that 2 implies 1?
It tells that this purity transformation is an isomorphism, provided that you have rigidity property,
yeah,
and the second arrow is an isomorphism.
Yeah.
And why do we need rigidity for that? What is format?
You need the other way around here, because I said that you have to prove that P. Yeah. You see here, P of F is a natural transformation of functor, and here you just have a map here. And to really prove that this is an isomorphism, you need to prove something about the tensor product by this object here, this one and this here. And this is where rigidity appears. But yeah. So the assertion is that a key fact is that if you apply this functor to F upper star to the unit object, then you get exactly this morphism here. This is what you have to check. So, and I should have done. I've said that this is checked if you want to see the proof. This is in the book with Denisha Selinsky. So. Triangulated category of motifs. It's an archive. It's not published. I hope it will be soon published. But actually, this theorem is stated for oriented theory, but it works the same for non-oriented theory. This is maybe why I'm not. So in the book, we were not aware that we could get this directly. As I said, because we were not aware that we could define isomorphism for non-oriented theory. But I think it will work the same for non-oriented things.
Our questions? That's fine.